Also, the enzymatic reactions reach equilibrium, but in the context of the pathway, that enzyme will not reach equilibrium. That is the reason. Okay. So that single arrow is specific only for the context of the pathway. So imagine that reaction looking like this: a large negative delta G, in which the enzyme is also slow. Means that A will be still there and makes a little bit of B during time. But since it's in a pathway, that B is becoming the substrate for another reaction, the next enzyme. So before that, there is enough B made in order to start the reverse process on the first reaction. That B will be eliminated because it will become C. Okay? So that is why those reactions that have only one arrow, that means they have a large and negative delta G, they cannot reach equilibrium in the context of it. So, and we look at this stuff, right? All reactions, and some of them that have a delta G close to 0 are in equilibrium, and this is the way to calculate it. So we should assume that when the overall delta G of the reaction is close to 0, those enzymes are actually able to go fastly in equilibrium and go back and forth.
He's 62 years old.
And this is how it looks like the reaction curve. So there is no huge difference from here to there. So in the first case, when the enzyme is far away from equilibrium, in most cases also the substrate and the K con M, the substrate has a lower value than the in concentration respect the K con M. I'm sorry. The K con M has a lower value respect the substrate. That means that not usually is not always, that reaction cannot be controlled by substrate concentration, because if the substrate concentration is like here, right? Even if you increase substrate, there is no huge changes in Dmax. So it has to be controlled in other ways. Those enzymes can have allosteric control. So there could be a molecule that is binding, those enzymes have an allosteric control. A molecule can bind the enzyme and make the enzyme working faster. There could be a covalent control. There could be a phosphorylation of the phosphorylation. But the substrate itself cannot very much regulate that. There is exceptions, and I will show you one, which is in a specific cell type, a specific enzyme. But in general, this is the situation. So these guys, these enzymes that have a large negative delta G, that needs to be regulated by complex types of regulation, they are considered like a dominant reader. They really control the flow of the reaction. They are the rate limiting enzymes. Okay? So if you change the speed of that enzyme by another molecule that activates and make an allosteric change in the enzyme, that will change all the pathway speed, because all the other enzymes are pretty fast. Okay? So the other implication in all this is that I'm reiterating too much of the same things. So it's like this pathway is like a mix of these reactions here and there, and a bunch of these with the violet stars. So, just to go back, the flux is the difference from the velocity at the end and minus the forward and the velocity of the reverse. And these guys that are the rate limiting are the slowest ones, so the flux could be basically the forward reaction only in this case. This is the glycolysis, the 10 reactions of the glycolysis. And if you see, there is a bunch of enzymes that have a close to zero, delta G0 or delta G. Those are those enzymes that I meant work really close to equilibrium. But then there is others, the first, the third, and the last one. So there is 3 in this case, that are far from equilibrium. So when we are going next lecture to look more at this pathway, we will focus on those 3 enzymes. We have to learn all about everyone, each single one, but more about those because they are the target of regulation. The other thing that what I said is actually telling us is that if you have a bunch of enzymes that making a pathway, and you have only 2 that are very slow, and all the others are work at equilibrium, if you want to make, and we're talking, let's say, glycolysis, if you want to make a gluconeogenesis, which is the opposite, so from pyruvate to glucose, we do that too. We need to make 10 completely different enzymes that work in the opposite direction, or we can have all the current enzymes working in the opposite direction, or else. So the second point is impossible because we know that 2 or actually 3 enzymes of a glycolysis are so slow that can go only one way. Thinking that we can revert that function by some regulation, no way. On the other side, saying that we need to make 10 other different, completely different enzymes, all made that can work backwards to make gluconeogenesis is also wrong, because it will be a waste. We have 7 out of 10 enzymes that work at equilibrium. They are basically ships that needs to be told what they need to do. And what is telling them to do, what to do, is a specific enzyme that is far from equilibrium. So if a glycolysis has those 3 enzymes far from equilibrium, gluconeogenesis can have just changing those enzymes into other enzymes and keeping everyone else the same. They can just change the direction of gluconeogenesis and make gluconeogenesis. So let's look here. I know that it's small, but I think we can appreciate that. If you see here, this enzyme, that enzyme, this other one, this, that, and this, 7, they are all the same, and they can work both directions. They work in glycolysis when this enzyme is working, that enzyme is working, this other. They work into gluconeogenesis when these other guys are working. So what that means, that for example, hexokinase, the first enzyme of glycolysis, is not used when we do gluconeogenesis, and we have a glucose 6-phosphatase, which is the last enzyme of gluconeogenesis. This is far from equilibrium with a negative delta G. This is far from equilibrium with a negative delta G as well. But they work in opposite directions. So if we wanna, you remember DNA, both strains, so this is kind of, there is no complementarity, but one is going this way, so this is the first, and this is the 10th. This is the first reaction of a gluconeogenesis, and this is the last one. The first reaction is pyruvate carboxylase, is the enzyme that is mediating that. And this enzyme is far from equilibrium as well. So that is the concept. We have loops here, which we will understand later what they do. They are target of regulation. They are the best way we can regulate those two boundaries. Because we cannot really, in the same cell, run glycolysis and gluconeogenesis on the same time. It's like building a house and then destroying the house to build the house again. Doesn't make sense. You want to have glycolysis when you need energy, and gluconeogenesis when you need to save energy or build something else. Okay? So all this offer a lot of way we can regulate the pathways. And here I tried to summarize all those ways. I apologize for the black on red, which is not great to see. I tried to change the last minute hours, but I forgot about this. This one, substrate level control, we will see examples of that. Is a beautiful way to regulate a pathway. Is not generally used for enzymes that are functional police. And is when the product of reaction can act on the enzyme itself because of some form of affinity for the enzyme, push it to the opposite direction. While this other mechanism, product inhibition, the product will be the end part of the pathway, which can inhibit the initial enzyme. Covalent modification, phosphorylation or dephosphorylation of the enzyme. Substrate cycles, this one is cool stuff, and if you look here, these are substrate cycles or metabolic cycles. We will study more of that when it's time, because today will be too much. And then there is also genetic control. That is the genetic way to control metabolism. Is increasing the amount of enzyme or decreasing the amount of enzyme because you make new enzyme. This is the slowest one. It can take weeks to be activated, not even days. So that is not something that works quickly during metabolism. So we are reaching the end. With most of hope, you can start your weekend faster. I know it's I like sometimes I like these big picture lectures. You don't have to put them in a side. Some of you really, because it's personal character and way to learn. Some of you might really like this way, others like the specific examples. Either way, use these type of lectures and put them in the context, because later on you will find examples. So what we are going to do now is just a brief talk about ATP and what it's doing and the reason why ATP is this molecule that gives us so much energy. It's not only ATP, there is also, we will see, NADH and NADPH, they are also a form of energy in another way. ATP can be made in two ways in our body. By directly phosphorylating ADP, so adding a phosphate group by an enzyme, which glycolysis does, but in a small amount, or by auxiliary phosphorylation, that is what the big process that happens in the mitochondria. Makes a lot of ATP molecules for each glucose that we start with. The way ATP is used, we saw already that chaperones use ATP, for example. We saw ATP in muscle contraction. We saw ATP in transmembrane transport, so molecules that can transport molecule against gradient. ATP is also used in the pathways, like the metabolic pathways, because some of them need a little extra help to go in one direction or the other. ATP molecule release a lot of energy by just eliminating this phosphate in one of the past lectures, we went also specifically showing what mechanism and why there is this large release of energy. But this doesn't mean that ATP is unstable. ATP is a very stable molecule. It's only by means of enzymes that phosphate can be released and energy can be harnessed to do something else. Especially the release of the first, or the gamma phosphate and the beta phosphate release of 30 plus kilojoules per mole. When you release this last one, I think it's 14 kilojoules, and usually it's not seen very frequently in metabolism. We will see this slide when we finish glycolysis. During glycolysis, we will make some ATP molecules. How we make that is because all the steps of glycolysis are done to just build the molecules that have energy that goes above the ATP. Phosphanol pyruvate and 1,3-phosphoglycerate, they are molecules that are made during glycolysis. And when they release their own phosphate, they will make ATP. So instead of taking in our cells a bunch of glucose and put it on fire and get the same energy out, but it is lost, we transform that molecule bit by bit until we make energetic molecules that once are broken apart, they can produce the energy to make ATP. And that is the direct phosphorylation of ATP. So I guess with this is, and by the way, we invest, during glycolysis, we invest a few molecules of ATP to do this transformation, but by the second part of glycolysis, we will get not 2, but 4 molecules of ATP. And that is basically what we are going to do in the next lecture and the next 2 lectures. So the last thing I want to mention, guys, is coupled reactions. In our way, we will see that some reaction is not able to go in the direction it should go, because its delta G is actually positive. So how we can fix that? The way is to couple that reaction with another reaction that has a larger and negative delta G. And there is 2 ways to do this. The simple way that you can visualize is connecting hydrolysis of ATP with that enzyme. Because that hydrolysis of ATP releases 30 kilojoules that are usually enough to revert the overall delta G. But there is other reactions that are even less easy to understand. They don't have ATP, but they are 2 different enzymes, really 2 different enzymes. And the 2 enzymes, one has a slightly positive delta G, but the next one has a larger delta G. And the 2 are working together that in a way brings the overall delta G of the 2 reactions on the negative side. And so they can move forward as well. And we will see those examples here. So that is what is for today. Study guide, study base counts. Please do your own work for that. Enjoy the weekend.